everyone, this is Professor Caravillian, and this video is going to cover our lecture for our organic chemistry lab on stereochemistry. So around the 1950s, stereochemistry came into big effect when there was a drug called thalidomide that women were using for morning sickness. And after a while, they realized that this drug is causing birth defects in some women, and in others, it was helping with their morning sickness. So they realized that within the drug were two stereoisomers. And if you recall, isomers are different compounds with the same molecular formula. So they realized that one stereoisomer was actually helping the morning sickness, and the other stereoisomer was causing the birth defects. So that's when stereochemistry took into a big effect. So what we had to do was start viewing these isomers in 3D images to see which stereoisomer was actually present. So when I mention stereochemistry, that is the 3D structure of the molecules, and we get to study this and see what kind of effect it will have. It has a major role in biological systems, obviously, so that's where we go back into medications, right? If something is not processed the correct way, it's going to be toxic to us, and we don't want any such thing like that present nowadays. So when we are doing our stereochemistry, we have to be drawing in 3D format. So on a paper, how do you actually draw 3D? So we use these flying wedge projections. It is a 3D representation of our molecules on a paper. So how we draw this is we have our regular solid lines that is on the plane of the paper. So you guys see here the hydrogen bonded to the center carbon. Sorry, this one and here. Those two are in the plane of the paper, and then we have our dashed broken line that's going away from the paper, and that's the carbon bonded to the chlorine right here. And then we have our solid thick line that gradually gets bigger. That is coming towards us, so it's coming out of the paper. So if you can try to picture this, the two yellow lines are in plane of the paper, and then the dash line is going away from the paper, so it's like going towards the back of the paper, and then the solid thick line, the wedge line, is coming towards us, so it's like coming out of the paper. So we will learn to make distinction between various kinds of isomers, especially stereoisomers. So as I mentioned before, isomers are different compounds with same molecular formula. That gets broken down into two branches. We have the constitutional isomers or structural isomers, and those are isomers that differ in the connectivity of their atoms. And then we have our stereoisomers, which are isomers with difference in 3D arrangement only. Stereoisomers get broken down into two categories. We have the conformational isomers and the configurational isomers. The conformational isomers are isomers which are readily converted into each other through a single bond, and then configurational isomers have no rotation possible through a single bond. So they could have the double bonds present. Configurational isomers break down into two more categories. We have the geometrical or cis and trans isomers, and then we have our optical isomers. So optical activity. So ordinary light is composed of rays of different wavelengths, the vibrating in all directions. And these vibrations can be made to occur in a single plane by passing ordinary light through the polarizer. So we have our light source, and we have the rays going in all different vibrating in different directions, and then we have our polarizer. So once it passes through the polarizer, it will go through a sample tube containing some kind of organic molecules. So we will view through the analyzer and see if this molecule pretty much kinks to the right or to the left. So if before I get into the right or the left, the compounds which rotate the plane are called optically active compounds, and the property is known as optical activity. Okay. So if it rotates to the right, we denote that by plus or the D, and that is because it's called dextrorotatory. And if it rotates to the left, we denote it by a minus sign or the letter L, and that is called the levorotatory. A lot of times how I memorize this is like in your car when you're listening to music and you want to turn the volume up, right? So you turn the knob to the right. When you turn it to the right, you're increasing the volume. So I remember as right plus, and if you're turning it to the left, you're lowering the volume, so minus, you're lowering it. So I remember left minus. So optical rotation is the change in the angle of the plane of polarization, and this is measured by this device called the polarimeter. And we measure specific rotation, which is the angle that's denoted by the alpha here. So however much angle it rotated is calculated by the specific rotation. Then we are going to go into chirality. So the term chiral comes from the Greek word here. I don't know if I'm saying that right. It means hand. So an object can have right-handed or left-handed forms. If you guys look on the image below, where you see the left hand and the right hand, if you put your hands together like you're about to clap, right, you see that your hands are a mirror image to each other, right? When your pinky comes to your pinky, your thumb comes to your thumb when you're clapping. But when you put your left hand, or should I say you put your left hand on top of your right hand, that's the image on this right side where you see the red and the blue. So you're placing your left hand on top of your right hand, and you see that your fingers don't line up, right? So this means that so your hands are a mirror image, but you cannot superimpose them. You cannot put them on top of one another and expect all your fingers to be in the right place. So if you can't superimpose that, then we call it chiral. That is called chiral. An object is chiral. But if you are able to superimpose them, for example, this butterfly image here. So if we cut the butterfly in half and we take the mirror image, right? Or if we take one butterfly and place it on top of another butterfly, they're superimposable. So if they're a mirror image positive and they're also superimposable, then they're achiral. And when you're achiral, you have a plane of symmetry. Then we have enantiomers. Enantiomers are molecules that have one carbon with 4 different substituents, and they have non-superimposable mirror images. So let me go over these examples. We have our first example here. Center carbon is bonded to 3 hydrogens and then an X, right? So the X is shown by the red sphere here. We see that the mirror image, so this blue area is technically the mirror image of the molecule. We see that when we place the mirror image on top of the original, it's superimposable, so therefore it's achiral. On our next example, we have the center carbon here bonded to 2 green hydrogens, and then we have a molecule, an atom of Y and X. So Y is the blue sphere, X is the red sphere. And we look at the mirror image and we see that, can we superimpose these? So if I take this left molecule and place it on top of this right molecule, it's not going to line up, right? It's going to be like our hands. So therefore, we have a chiral molecule, but we do not have a chiral center. And why is that? Because a chiral center has to be bonded to 4 different molecules. So if you look at our last example here, we have our center carbon bonded to hydrogen, bonded to Z, Y, and X. The center carbon is bonded to all different elements. I mean, I don't know, it could be molecules, it could be anything. So if I take this image and place it on top of the mirror image, they do not line up, right? So that's why we have a chiral molecule. And because the center carbon is bonded to 4 different things, we have a chiral center. So if you have a chiral center, and when you draw out your molecule on your paper in 3D image, your chiral center gets an asterisk. That is denoted that we have a stereocenter. So how do we calculate the number of stereoisomers? What we do is we take the number of chiral centers, carbons that we have, and the equation is 2 to the power of n. N is the number of chiral carbons. So for this above example, it's 1. So it would be 2 to the power of 1. Let me write that here. 2 to the power of 1, and that is equal to 2. So let's do some examples here. So our first example here, we have our center carbon bonded to 4 different molecules. So therefore our center carbon is chiral, so I denote that by the asterisk. Then we calculate our stereoisomers by the equation 2 to the power of n. So 2 to the power of 1 is equal to 2, so there will be 2 stereoisomers of this molecule. Our second example, you see here we have the 2 hydrogens. So our center carbon is obviously not bonded to 4 different. Therefore, it's achiral. So we do not have a chiral center. That's where we get the 0 from. So 2 to the power of 0 is equal to 1. Therefore, we have 1 stereoisomer. The next example we have, similar to our first one, center carbon is bonded to 4 different molecules. That's why it's chiral. Then our fourth example, we have here center carbon double bonded to oxygen, and then we have 2 more bonds here. So because we only have 3 bonds, okay, I know this is double bond, but it's only bonded to 1 oxygen. So we have center carbon bonded to 3 groups. Therefore, it cannot have a chiral center because by definition the chiral center carbon needs to be bonded to 4 different groups. Therefore, this example is achiral. So 2 to the power of n will be 2 to the power of 0 is equal to 1. We have 1 stereoisomer. Now we get to the challenging. examples. So if you look at here, how I do these is I break this, let me use, okay, those of you that know my pen is working sometimes it's not. What color do I want to use? Pick a color. Green. Okay. Alright, so what I do is I break this in half. If it wants to write. Okay, there you go. So, we have this center carbon here, right, is bonded to a CHO, bonded to an OH, bonded to an H, and then it's bonded to this whole bottom piece. Okay, so that's where I get, so since each of these groups are different, that's where I get the first asterisk from. Okay, so then I do the same thing for the bottom half. So let me erase this. Now, split in half. So now for the bottom carbon, I have bonded here to a hydrogen on the left side. My pen won't write. Okay, we have an OH, we have CH2OH, and then we have on top this whole big group. So every group is different. That's where I get the second chiral center from. So this molecule has 2 chiral center carbons. When we put it into our 2n equation, it's 2 to the power of 2, which is equal to 4. Therefore, we can have 4 stereoisomers of this molecule. So our next example, now it gets even bigger. So now, let me zoom in. Okay, so we have, I'm going to do the same thing. I'm going to break in between the 2 carbons. So, and then I'm going to break in the next 2 carbons. Okay, let me use another color so you guys see better. So for our first carbon, right here, I have an OH group, CHO group, a hydrogen group, and then I have all of this bonded. Okay, so that's 3 different groups. That's where I get this first asterisk from. Okay, now we do the same thing for the second one. So now for this carbon, right, I have bonded to an hydrogen, an OH group, and then I have this whole big group here up here, and then this group down here. And they're both different, right? We have a CHO up here and we have CH2OH down here, so they're both different. That's where I get our second chiral center from. And then do the same thing for the bottom. So we have CH2OH here, we have a hydrogen and an OH group, and then we have bonded to this entire top. And that's where I get the third chiral center from. So since we have 3 chiral centers, we have 2n equation is equal to 2 to the power of 3, and we get 8 stereoisomers. So going over, stereoisomers are having the same molecular formula but different arrangements of their atoms. I believe there's 4 kinds that I'm going to go over. We have our enantiomers, which are stereoisomers, which are non-superimposable mirror images of each other. So chirality is obviously necessary and sufficient condition for existence of enantiomers. They always exist as discrete pairs. So if we look at the dotted line, that's our mirror line. So we have our molecule on the left side, and then on the right side is the mirror image. So if we take these and we superimpose them, they're not superimposable, right? Then we have our diastereomers, which are stereoisomers that are not mirror images of each other. So, okay. So for here, remember the example I went over where we had the 2 chiral centers, right? So we have here 2 chiral centers. So if we do our equation 2n, which is 2 to the power of 2, oops, that gives us four stereoisomers, right? That's where we get our A, B, C, and D. So we have 4 stereoisomers. That means we can have this molecule in 4 different possible ways. So on our first one, we see that if we take the mirror image, right? So we take the mirror image, which is an enantiomer, and then we'll place it on top of another stereoisomer, and it won't obviously be placed because all 4 of them are different. So they are not mirror images of each other. So if I take B and C, right, they're not mirror images, so they're different. We can't like put them like our hands together like a clapwise. Nothing's gonna line up. Nothing. Does that make sense, guys? So A and B are mirror images, C and D are mirror images, but B and C are not. A and D are not. Do you guys see that? Like, some of them can be, but not all of them. So these are diastereomers. Okay, now we have number 3, geometrical isomers. It occurs as a result of restricted rotation about a carbon-carbon bond. Okay, so if we have a double bond present, right, we cannot rotate anything. So when we have our double bonds present, we have our cis and trans isomers present. So how I remember this is cis, right? Cis, same, cis, same. So cis is the same side. So the molecules that are bonded would be on the same side. And for trans, it would be on the opposite side. So if we were looking for, let me see. If we were drawing this in on a piece of paper, obviously for cis, you would have them coming in the same direction. So either both of your wedges are going to be solid, okay, or they're both going to be dashed. They both have to match for cis. And for trans, obviously they have to be different. So one is coming towards you, one is going away from you. For cis, this image we have here, they're both coming towards you. If it was the dash, they would be both going away from you. Number 4 is conformational isomers. These are isomers that can be converted into one another by rotation around a single bond. So we have 3 examples. We have eclipsed, gauche, and anti. Let me go over. Eclipsed is pretty much 0 degrees, so everything is lined up. Gauche is 60 degrees from one another, and anti, okay, it's 180 degrees from one another. So if we look at these Newman projection, right, these eye-looking things here, they're called Newman projection. I don't know if you went over it in your lecture. So for eclipsed, we have our 2 methyl groups that are lined up. So we draw it like this because we don't have space to write the CH3s, but this is pretty much 0 degrees apart. 0 degrees apart. And then for gauche, we have here, it obviously rotated, right? And that rotated 60 degrees, so that's 60 degrees. And then for anti, so we went from up here all the way down here, that rotated 180 degrees. So if you're having a hard time picturing this in your mind, this sawhorse formula will help you visualize it. So for our eclipsed, we have the 2 methyl groups, which are the black spheres, right? These, they line up, right? They're on the same. There's no rotation between them. Then we can rotate, well, for here, it's rotating to the left, but for our Newman projection, we rotate it to the right, but you got the point. So we rotate it. So originally it was here, right? And we rotate it to the left. And that is our 60 degrees. This is 0 degrees. And then for our anti-conformation, we rotated, so we started off here. We rotated 180 degrees, so that's where we ended to the bottom, and that's the 180 degrees. So if you can rotate, right, they're called conformational isomers, so you can rotate them around. So that's the end of our stereochemistry 3D understanding of the molecules. So you have to finish up this packet stereochemistry worksheet. If you need to refer back to my video, go ahead. Otherwise, you have a page on Canvas that gives you all the definitions. So while you're doing the packet, and if you feel like you don't remember what each word was, you can refer to that page of definitions and have a better understanding. But you having this background information, you should be able to complete that packet with no issues. You can use your partner if you like to. You should. But please do not submit the same packet to me. Make sure each of you do your own work and submit it on Canvas. So that's it for today. I will see you guys next week.